via
I see, yes, thank you.
So if you do not mind, I'll start. Dear colleagues, greetings. It's almost exactly, we are in the middle of spring, and our today's seminar is dedicated to the World Quantum Day, which was yesterday. And it's my great pleasure to have our guest, William Oliver, today with the talk Emulating the Bose-Hubbard Model with Arrays of Superconducting Qubits. And with one slide, I would like to introduce Will to the audience. William Oliver received his PhD degree in electrical engineering from Stanford University, his master's degree in electrical engineering and computer science from MIT, and a bachelor degree, first one in electrical engineering, and Bachelor of Arts in Japanese from the University of Rochester. For some 20 years, William worked at Lincoln Laboratory with the Quantum Information and Integrated Nanosystems Group. Now, William is jointly appointed the Professor of Electrical Engineering and Computer Science and also Professor of Physics at the MIT. He serves as the Director of the Center for Quantum Engineering and as Associate Director of the Research Laboratory of Electronics. He is a principal investigator in the Engineering Quantum Systems Group. Will has research interests in material growth, fabrication, design, and measurement of superconducting qubits, as well as in the development of cryogenic packaging and control electronics involving cryogenic CMOS and single flux quantum digital logic. Professor Oliver is a fellow of AAS and APS, a senior member of the IEEE, and serves on the National Quantum Initiative Advisory Committee. With this, I would like to give the microphone to Professor William Oliver. Please.
Great. Thank you very much, Sergey. It's a pleasure to be here. And let me just make sure confirm the screen looks okay to you on your side.
Yes, perfect.
Okay, great. Yeah, very good to see you, Sergey. We've had many collaborations and discussions over the years, and particularly on things related to Landau-Zener and control using Landau-Zener transitions. And it had been my hope to actually visit one day to Kharkiv, and I still hope to do that. But today, if you'll allow me to present remotely, thank you again for the invitation to speak. And what I'd like to talk about today is emulating Bose-Hubbard models with arrays of superconducting qubits. And then towards the end, I'll, I guess maybe in honor of International Quantum Day, also talk a bit about where we are with high fidelity gates and quantum error correction. So by way of introduction to qubits, just very generally, they basically come in two flavors. One, of course, are the natural atoms that nature gives us. And this is, of course, periodic table of elements. It is 100 years that we're celebrating of quantum, and of course, some of our famous people like Niels Bohr and Chadwick shown here. But these elements, of course, we know have very different behaviors depending on the number of protons, neutrons, and electrons in them. Most of the qubit elements are over here in the left two columns for neutral atoms and for trapped ions, but not all of them. There can be other ones. So those are natural atoms or natural qubits. The artificial atoms or artificial qubits are made from inductors, capacitors, and Josephson junctions, and we can arrange them in different numbers and with different values to create electrical circuits that exhibit quantized energy levels at low temperatures. And in some ways, not always, but in some ways behave like an atom. So we call it an artificial atom. I'll talk more about this later, but this circuit that you see here with a Josephson junction and a capacitor is perhaps our simplest qubit, superconducting qubit, and maybe we can think of it as the hydrogen atom. It's the simplest. And it's one of a family of different qubits that we can make with different numbers of inductors, capacitors, et cetera. And so these superconducting qubits that I'll talk about today are artificial atoms. They have properties that we can design, and we do design them to make them sensitive to different levels of noise and different types of noise. So superconducting qubits are just one of these many modalities. And what I'm showing here on this chart is the number of operations before an error on the left vertical axis. On the right vertical axis is the gate fidelity, which is basically 1-to-1 in this number of operations before an error. So if there's one error out of 100 gates, that's 99% fidelity, and 1 in 1,000 is 99.9%, et cetera. And of course, higher fidelity gates are better. The horizontal axis is the speed with which I can apply gates. And what I'm showing here are the 1 and 2 qubit gates that we use to implement arbitrary quantum logic. So with a series of 1 and 2 qubit gates, we can implement any quantum algorithm. And this chart is basically to give us an idea of how the different technologies relate to one another or stack up against one another. And one of the major ones today are trapped ions. And you can see that they have fairly high fidelities, particularly single qubit gates, but they're relatively slow. And so their goal today is to try to get faster. I work with superconducting qubits, and our speed is already pretty high, relatively speaking, but we would like to improve fidelities. I'll speak a little bit about that at the end. Another major contender, an upcoming one, is neutral atoms that sit somewhere in between. And of course, also silicon quantum dots, nitrogen vacancy defect centers. Not shown here are photonic qubits. So there are many modalities, and I would say the common theme is that they're all trying to get to this upper right corner: fast performance, high fidelity. And it's not just about gates, it's also about measurements. And if we look at the times it takes to, say, reload or to measure neutral atoms, trapped ions, or superconducting qubits, which is necessary to do quantum error correction, then these speeds become even slower. And so roughly speaking, an error-corrected qubit machine from superconductors would operate at about 1 megahertz. And to do that from, say, a natural atom would be around 1 kilohertz. Now, of course, people are trying to make that faster, but that's basically, from my perspective, where it stands today. So I won't talk or cite all of this work worldwide. There is a lot of effort going on. Which one is going to be the winner in the end? Probably not one winner, right? Probably in the early days, it'll be superconductors and trapped ions. Later, it may be a different technology that shows either better or more convenient performance. This is what these processors look like today. In the lower left is IBM's Osprey. This is a 430-something qubit machine. You can see that it's 3D integrated. It's superconducting. The upper left is Google's Quantum AI Willow processor. And I'll talk a bit at the end about the Willow processor and how it was used last fall to demonstrate the scaling of quantum error correction. In the middle is a neutral atom quantum computer from a startup called QEra, comes out of Harvard and MIT. And inside this magneto-optical trap is where those atoms reside. This Quantinuum H1 is a trapped ion system. You can see a racetrack here. And on this racetrack, the trapped ions can circulate around, and then they talk to each other through these bridges that branch across the different arms of the oval. In the lower right is a D-wave quantum annealing machine, also superconducting, but not of the gate model type, quantum annealing type. And of course, in the lower middle here, this is obviously not a quantum computer. This is the Wright Flyer. It was the first airplane to fly that was self-propelled, and there was a person on board who was steering it. It wasn't the first time we flew, of course. We had hot air balloons and aerodromes and the like, but this was the first time where it all came together. And even though it only flew maybe 100 meters at most, and it wasn't very high off the ground, I think when we looked at this, we understood that commercial aviation would happen. And it might take 20 or 30 years, but it did come. And I put this picture here because I believe many of the processors that we see around the outside, these are at this stage where they're still very primitive, but I think we can understand that commercial quantum computing will happen. So there's a lot of promise to quantum computing, but to realize the promise, we need to engineer systems that are robust, reproducible, and extensible. And it's going to take some time, but I think we're on our path. So with that as a International Quantum Day introduction, let me get into a little more technical aspect to the talk. And what I'd like to introduce are superconducting artificial atoms in a little more detail than before. And to start with, we can look at this harmonic oscillator in LC circuit, L for inductor, C for capacitor. And we know that this is an example of a simple harmonic oscillator, meaning that the potential of this circuit is proportional to either current squared or voltage squared, or in different units, we could call it the phase across the inductor. And it's parabolic. And one property we know of a parabolic potential is that the quantized energy levels are all equally spaced. Now, in this case, the energy separation is Planck's constant times the resonance frequency of the resonator. Okay. And we can see, in fact, when we cool this down to sufficiently low temperatures, where kT, the thermal energy, is much less than this energy separation, that indeed this electrical circuit has quantized energy levels. But the issue is that if I try to operate within a 0-1 manifold, which we would call a qubit with two levels, because the energy transitions are degenerate, driving 0 to 1 would also drive 1 to 2 and then 2 to 3, and very quickly we get outside the qubit manifold. So we have to make the potential anharmonic in some way. And we could choose either the inductor or capacitor, but we choose to make the inductor nonlinear because a Josephson junction gives us that almost for free in superconducting qubits. So the Josephson junction are two superconducting leads with an insulator. And we know the Josephson relations for the current and the voltage are shown here. But from our purposes, what we care about mostly is the inductance. And so if we define the inductance in the usual way as an electrical engineer would, we can solve for it, and we find that this inductance now is a function of the current that goes through the inductor. And it relates to it through this cosine phi. That means the inductance is nonlinear. It's nonlinear in the current. Different currents yield different values of inductance. We can then go back and ask, what is that potential profile for this junction, LC, this current, this circuit, the current and the voltage. And we find that it now has a cosine type potential, which is anharmonic. And that's how we come up with this, what I called hydrogen atom before, but our transmon circuit developed at Yale around 2007, 6, 7, something like that. And so this is an LC circuit, but the L is now a Josephson junction and it's nonlinear. And what that means is that rather than this red harmonic potential, quadratic potential, we now have the cosine potential in blue. And the consequence is that the 1-2 transition is no longer degenerate with 0-1. And because of this, we can uniquely drive the 0-1 transition. Okay, so many superconducting qubits are derived from this concept. Again, this is the simplest case, but we can add more junctions, add more capacitance, add additional inductance and linear inductance to come up with an array or a Mendeleev table of superconducting qubits. Now, we typically operate them at lower frequencies, meaning maybe 5 gigahertz, certainly lower compared with natural atoms. And so this necessitates that we operate in a dilution refrigerator. So if our qubit has 5 gigahertz, then the thermal energy of that is about 250 millikelvin. And that means in that environment, the qubit would be thermally excited. And we'd like to avoid that. It's not impossible to work in that regime, but to avoid it, if we can even go 10 times colder then because the temperature comes in an Arrhenius function in the exponent, the excitations are highly suppressed. And so we'll operate at 20 millikelvin. This is a dilution refrigerator cold plate, about 0.5 meter in diameter and 0.5 meter deep. And you can see many of the components that we use here, filters, switches, attenuators, etc. Now, because we design these, we also then have to fabricate them. And we fabricate them using standard silicon fabrication technologies. So very much what the tools that are used to make CMOS, not all of them, but many of them, the etchers, the deposition tools, we'll use to fabricate qubits. This is a silicon technology. We use silicon wafers. This is 200 millimeter wafer. And just to show some pictures, what we're seeing here, there's 5 pluses, plus symbols, I guess, in a row. Each plus is a capacitor, and it's a capacitor to ground, so it's a lateral capacitor, not parallel plate in this case. You can see readout resonators going to the upper right, and then control lines to the lower left. But to see the inductor, we have to zoom in quite a bit. The capacitor is much larger. So we zoom in here, and we can see this capacitor now to ground in a little loop. And if we zoom in further, here's the loop. And what this loop is it's basically a squid. It has 2 Josephson junctions. And we make this squid because by applying a magnetic field and threading flux through the loop, we can tune the effective inductance of the squid and thereby tune the qubits frequency. And that's quite useful when we have qubits that are inside a refrigerator and we need to tune their frequency. And so if you zoom into the smallest scale size, which is still rather large compared to CMOS, we're talking 100 to 200 nanometers, you can see the actual Josephson junction itself. Okay, and we can break the plane by making bridges, and we can even 3D integrate, as I'll show in a bit. The way that we control the qubits is shown here, and what I'm illustrating is on the left, of course, the Bloch sphere with 0 at the North Pole and 1 at the South Pole. And on the right, or in the middle here, I'm showing the pulses that we apply. Now, these pulses are just the envelopes. I didn't put the high frequency component inside it. But these pulses that we apply are generated by IQ mixing. So there's a local oscillator tone, which is on all the time. And it gets multiplied using an IQ mixer with an intermediate frequency tone from an arbitrary waveform generator, which includes the pulse and the intermediate frequency. And that could be around 10 to 100 megahertz, the LO being up at around 5 gigahertz. And when those are multiplied together, we get a pulse that comes out at the LO plus or minus this intermediate frequency. And we'll filter it in such a way that we keep just one of them, and that is resonant with the 0-1 transition. Now, that's an electromagnetic pulse, so it goes in a coax cable down to the qubit, where it can be capacitively coupled to the qubit like this, or not shown, could also be mutually coupled via an inductor antenna. And by choosing the I or the Q port of the mixer, we can then rotate the qubit around either the x-axis of the Bloch sphere for in phase or the y-axis for the quadrature phase. And all that does, this mixer will just shift the carrier by 90 degrees. And so if you then look over here at the Bloch sphere, as we apply these pulses, you can see the rotations that occur. So we'll rotate around the x-axis, a pi. We rotate around the minus x-axis by pi. We now shift to the Q port, and we can rotate around the y-axis, and so on. And of course, half of the area only rotates half as far, so that's pi over 2. So with this, we've been able to, as a community, get more than 4 nines single qubit fidelity and more than 3 nines 2 qubit fidelities in few qubit systems. And by few, I mean between 2 and maybe 100 or so. Okay. And lastly, the name of the game for us is to improve coherence, because we are coherence limited, generally speaking. And so what makes this difficult, of course, is that there's a lot that goes into taking an idea to improve coherence and then acting upon it. And it starts with materials growth, analysis, modeling, of course, designing the devices, actually fabricating them in the fab facility, then doing some post-processing, looking at the test structures to make sure things worked, put it in a fridge, hook it up to the electronics, and then actually make a measurement just to see if that was a good idea or not. And of course, we eventually iterate this process to hopefully improve coherence. And that's basically, if I had to say so, this is basically the last 25 years of my research is just spinning around in a circle over and over again. Okay. And what I'm showing here on the left are some times that we've achieved at MIT and Lincoln Lab across many of the different types or family of qubits and superconducting qubits. But I don't want to imply that at all that we're the only ones doing this. This is actually research effort by groups worldwide. And this chart, in fact, comes from this paper from Kiergaard et al. It's a review paper. And in here, you can see many of the references to these many groups who have done this fantastic work, improving coherence times from the nanosecond level by Yasu Nakamura and the NEC group in 1999 to today we're over a millisecond with qubits like transmons and fluxonium. That's not shown here. These are some review papers here if you'd like to learn more. And these improvements were really a result of improvements to materials, fabrication, design, and not listed, but also control. So with that, let me transition now to the topic of Bose-Hubbard emulations. So one of the uses of a quantum computer is to simulate other quantum systems. To put this into context, there are many ways, of course, in physics that we can simulate or emulate quantum systems. On the right here is to build a quantum computer, and using a gate model, we write a program that simulates, I will use that word specifically here, simulates some other quantum system according to a prescription. And that could be something like trotterization of the Hamiltonian, chopping it up into small time pieces to look at the time evolution. At the other end, we can create, of course, systems like twisted bilayer graphene, where we take two graphene sheets and rotate them slightly with respect to one another to create a Moiré lattice. And in doing so, we can emulate, in some sense, or create a flat band system. Okay. And of course, that has very little control once you've created the device. It does have a backgate where you can tune the electron density, but it's much less control than over here on the right with a simulator, which could simulate in principle any system. And what we are doing here is we're somewhere in the middle. We're creating a system of qubits, either 9 or 16, and we tailor their energies, the on-site energy and their coupling energies, so that we can mimic the Bose-Hubbard model. So we have a higher degree of control, I'd say, than Moiré systems, for example, but not as much control as we would have in a simulator. So we're not the only ones to do quantum simulation, of course. This is done across many platforms. But our approach is called analog hybrid. So analog is in the sense that we're emulating a system, hybrid in the sense that to set up the system or to make it run more efficiently, sometimes we will use digital gates. And of the two, I would say that we are emulating a system. We're not necessarily simulating it. Okay, so we're using 9-qubit and 16-qubit lattices of qubits. Now, the features we have is that we have on-site control, X, Y, and Z, that we can implement simultaneously and uniquely across the lattice. We have always-on coupling, but we can detune qubits and drive them parametrically to turn on and off the coupling. We have site-resolved readout, also simultaneous, also unique to each qubit, and we mimic the Bose-Hubbard Hamiltonian. So to set this up, the transmon qubit that we will use is the same one that I showed before. And if we write the Hamiltonian down, one way to write it is to start with the harmonic oscillator term, written with creation and annihilation operators, and then add in a nonlinearity, a Duffing type nonlinearity, which we call anharmonicity. Okay. And that's an artificial atom. Now we can capacitively couple two of them together, and maybe we might call this an artificial molecule. This is now one coherent system of two qubits. And we can similarly write that Hamiltonian as in the same way that we have the harmonic oscillator terms. On the right, I didn't explicitly write it out, but for each qubit, it has its nonlinear anharmonicity. But important here is with this capacitor, we now have an exchange coupling between the two qubits, where it can exchange an excitation back and forth with a strength J when the qubits are on resonance with one another. And so the idea is to build up a lattice of qubits like this, where the dots are the qubits. Now, in this case, we'll make them with a squid rather than a single junction so that we can also tune the frequency of each qubit. That will become the on-site interaction. And then the coupling between qubits is the capacitance. Okay, and so this mimics the Bose-Hubbard model. I'll talk about that in more detail right now. So the Bose-Hubbard model, of course, has on-site interactions or energies. That's our qubit frequency. There's also, or the on-site energy. The on-site interaction of more than one excitation is shown here with a strength U, although as I'll mention in a moment, we're in the hardcore limit. And then the exchange interaction is shown here. And so we realize this with an array of in this case, 16 qubits. I just mentioned what these terms are in the Hamiltonian. To give some energy scales, we can tune our qubits between, say, 3 and 5 gigahertz. And our anharmonicity is about 200 megahertz. So to put in a second excitation, it turns out to be an attractive potential, but it's about 200 megahertz. But the exchange coupling is much smaller. The exchange coupling is about 6 megahertz. And so the consequence of that is that U is much larger than J. And that means that we will not excite a second excitation via the exchange coupling. And in the jargon, this means we are in the hardcore limit. It's a highly nonlinear case. And that's what we'll do today. So one of the first demonstrations we can do to show that this works is to do what's called a random walk in 2D. And so if you're in Manhattan, or if you've visited Manhattan, the streets are all perpendicular to one another. And if you want to go from, say, point B to point A, you have to take left turns and right turns, et cetera, and follow some path to get to that point. And our lattice, it's a similar story that if I put an excitation in qubit 1, I have to take several steps at right angles to get to, say, qubit 9 on the other side of the lattice. And so we can count those steps, 1, 2, 3, 4, and then plot what happens as a number of the steps when we put an excitation here at qubit 1, which I'm saying is step 0, and then look as a function of time on the vertical axis. And what we're seeing here is experiment on the left and the simulation on the right, and maybe not so exciting, but what happens is the excitation bounces over to qubit 9, comes back to qubit 1, goes back to qubit 9, et cetera, and just bounces back and forth. Now, part of the simplicity that we see here is because of this highly symmetric 3x3 array. We'll see later some more complicated examples of the dynamics that when we go to 4x4, it gets more complicated due to quantum interference. 3x3 in this sense is somewhat special, but it illustrates the point. So again, this is emulating the Bose-Hubbard model, and we're in the hardcore limit. Okay, so some recent work we've done with these types of chips are listed here. And what I'd like to talk about today is Anderson and Stark localization. I won't have time to talk about area law versus volume law, but then I'll talk about creating a synthetic magnetic field, an electromagnetic field in this system, and then some flat band physics. So for the localization experiments, we can emulate Anderson localization, both in 1D and in 2D. And in terms of disordering our lattice, what that means to us is that we detune the qubits to have different frequencies from one another. And the more that we detune them from one another, the larger this value delta, which is indicative of how much disorder there is. And so we can plot as a function of the disorder length something we call participation ratio. And that's basically a measure of how extended the quantum state is across all of the qubits. And so a large participation ratio happens when we're at low disorder, meaning the state is highly extended. But if we turn up the disorder strength, the participation goes down and becomes localized to one or just a few sites. Now we can look at 1D by detuning very, very strongly, much stronger than delta, a couple of the qubits so that we're only left with a 1D chain. We can also do this in 2D. And I'll explain more later, but we plot here the data, a theory fit, which means a theory of Bose-Hubbard model only, and then simulation, which is simulating the actual qubits that we have to see how consistent these are. The other thing we can do is we can apply a gradient to the qubit frequency, which looks like an electric field, call that F here. And in 1D, where we can only look at what's happening around the edge here, if I put an excitation in qubit 2, I can ask how it goes up the left and right arms. And in the presence of a gradient, the excitation attempts to make a random walk, and it does so a little bit, but eventually it comes back. And then it oscillates or breathes in this manner. And these are called block oscillations, which is a consequence of these Wannier-Stark ladders. And you could look at the localization in a similar way as we did above and show that it matches fairly well. We can also do that in 2 dimensions, where now we can apply a different electric field or the same electric field if we wish in the X and Y direction. And if we create an excitation here on the first qubit, again, this breathing or block oscillations occur, and we can mimic that and for different strengths of this slope. So this was basically some work we did back in 2022 to show that, okay, this seems to be working as we would expect. And since then, we've moved on to a 4x4 array. And let me highlight Cora, Amir, Sarah, and Ilan. Ilan was the postdoc who led this team on the experiments I'm about to show. And I won't read through all the numbers here on the left, but just to say that this 4x4, so 16 qubits, have these properties. The average T1 is about 20 microseconds, so that's not a world record, but sufficient to do what we wanted to do. And if we look at the fidelities of our operations when we do operations, single qubit operations, it's between 99.5 and 3 nines fidelity. And again, we're in the hardcore limit. So I mentioned before that we have squids and we need to apply a magnetic field to set the qubit frequency. That's just to operate the qubits. But many of the systems that we would like to analyze or emulate also themselves require a magnetic field. And it's sometimes a very, very strong magnetic field, such as one would achieve, say, with a vector magnet shown here. The types of experiments I'm thinking of would be, say, quantized Hall effect, right? Or some notion of topological superconductivity in the presence of a magnetic field. And so this is a second magnetic field. And of course, if we were to apply it directly to our qubits, the qubits themselves wouldn't work anymore. So we have to, here are a few other examples shown on the right. So we have to come up with a mechanism to effectively apply a magnetic field, but we're not actually applying it. It must be a synthetic magnetic field. So we need to emulate not just the system we're interested in, but we also need to emulate the magnetic field. That's my point. And so in a continuum model, we can talk about the vector potential that leads to electromagnetic fields, but we don't have a continuum model. We have a discrete model. And so we can do what's a Peierls substitution, where M is now the different lattice sites coupling neighbors and with a strength J. And we can obtain a phase or implement a phase here. And that phase is the analog in a discrete lattice of the continuous vector potential. So whereas we have a discrete or a direct transverse coupling in the case of this lattice on the left, the way that we implement the phase is in fact to first detune the qubits so that they're at a different frequency. And now they don't have a direct exchange coupling because they're at different frequencies. But we can then couple them by turning on an electromagnetic field driving the system with a frequency that is exactly the detuning frequency. Here we call it delta. And if we drive with a phase phi, that phase becomes this Peierls phase. Okay, so that's how we implement the phase, by driving a qubit or coupling neighboring qubits. And the rate now, the exchange coupling is happening related to this amplitude that we're of the driving field, and of course exhibits also a Bessel function dependence. So we can set the Peierls phases in our lattice by parametrically driving, that's what we call this, parametric driving, of superconducting qubits, and that allows us to emulate a magnetic vector potential. Okay, and from that allows us to get a magnetic field. So here's what it looks like. This is called Aronoff-Bohm caging. It's basically interferometry. And the case I'm showing here, there is no synthetic magnetic field. And we'll put an excitation on qubit 1 and ask what does it look like to get to qubit 4? And what we're plotting here, qubit 4 is orange, and you can see that the excitation goes to qubit 4, and it goes back where? To qubit 1. And it basically just exchanges back and forth as we would expect. Maybe it's easier to see in the visualization where the excitation's on the left, goes to the right, comes back to the left, etc. So this is just a standard interferometer, or you could think of it as a simple random walk. But what we could do is instead detune these qubits and then couple them together using this Peierls phase pi, and now the upper path and the lower path differ by pi, which means that that should have a destructive interference by the time we get to qubit 4. And so as you can see, in orange, there's a little bit, okay, it's not perfect, but very little of the initial excitation arrives at qubit 4. And you can see that here in this color scheme again, where very little of this dark color ends up over here on the right at qubit 4. Okay, so this is, again, Aronoff-Bohm caging implemented using a synthetic magnetic field from the Peierls phase. Okay, so this is for one example, pi. We can, of course, choose any phase that we want, and so if we now plot on the vertical axis the phase, here is 0 where there's no phase, and then at the extreme of plus or minus pi, and then ask the question, how much of that excitation gets to qubit 4, and that's the color scale here. And at 0, of course, the excitation entirely, or almost entirely, gets to qubit 4, and it oscillates back and forth. But if we go to pi, now it remains dark. Very little of that excitation, if any, gets there. We can now simulate the qubits that we have. We characterize their frequency, their coherence time. We characterize how much they're detuned from one another, their specific couplings, J. They're not all exactly the same because we fabricate it. And that's what we get. We can then say, let's imagine this is an ideal Bose-Hubbard type model, in this case called Harper-Hofstadter model. And what we see is this actually looks pretty close. And what that tells us is that our goal of emulating a Bose-Hubbard model is actually pretty good with these qubits. And this is an indication of how good it is and also where it deviates a little bit. So that's why we do these different simulations. We can also measure and look at the excitations of these intermediate qubits as well as where we started. We can go to bigger rings, of course, because we have 16 qubits. What I'm showing here is now basically 3 qubits on an arm, each arm. And you can see here again the experiment, the simulation of the qubits themselves, and then the numerical simulation of the model. And we see that things match pretty well. And again, when our Peierls phase is pi, very little of the excitation gets to the right side. We can go to a 4x4, and it's the same story. Again, when we have a Peierls phase of pi, very little gets there to the other side of the lattice. But now what we see is the agreement between the model and our qubits is not as good. When we simulate our qubits, this matches fairly well because we're actually simulating the actual qubits we have. But due to small imperfections, essentially maybe we're not calibrating quite as precisely as we should, there is a slight difference between our qubits and the model that we're trying to edit. It's close, but not perfect. And you can see some of the differences here. Okay. So with a magnetic field, of course, we would expect that we have gauge invariance. And there's a way that we can test this or look at it. And let's imagine the same experiment now with 3 qubits on an arm. And we're going to put a Peierls phase phi here, which means we have phi within this loop. And this is in a directed sense around this loop. We can move that phase to another pair of qubits and nothing should change. And indeed, if you look at the experimental results, nothing has changed here. We could move it to another pair of qubits and nothing changes. We could divide that up into 3 pieces, and as long as around the loop it still equals the same magnetic field phi, that's a phi threading the loop or a magnetic flux, again, nothing has changed. Of course, we can make it change. We could put on one arm plus phi and on another arm minus phi in this directed sense, and now it goes back to looking like there's no magnetic field applied. Okay, and so this is an illustration of gauge invariance of our synthetic vector potential. Okay, so with a vector potential, of course, we can also create an electric field. This was due to Faraday's law. If we take a 1D chain around the outside of our 4x4, we put an excitation in the middle. We've seen this experiment already. And basically, you'll have a random walk in each direction, and you can see it happening here. A little more complicated than the simple case of 2D just bouncing back and forth, but basically, this is what this interference pattern looks like. Now, if we want to do Wannier-Stark type disorder, putting a gradient on the lattice, that means we need an electric field. And again, using the same concept, we know that the electric field in a continuum sense is the time derivative of the vector potential. So in a discrete sense, it will be the time derivative of the Peierls phase, right? And that allows us to now create or mimic an electric field. And we're showing again here now Wannier-Stark localization, where the strength of our electric field or the degree, the slope of our qubit frequencies in this sense, is emulated here, and you can see the breathing due to the block oscillations in our qubits. Okay, so this also works. Good. So with that, we now have some tools in our toolbox to actually go out and emulate another physical system. And one that we wanted to do was to look at a system that exhibits flat bands in one dimension. Okay, so this looks like 2 dimensions, but just left to right, it's a one-dimensional system. And we call it a rhombus lattice. So there's 3 of these rhombus plaquettes. And when the phase, the Peierls phase or the magnetic flux through each loop is the same, it will always be the same in this experiment, but when we set it to 0, we have 3 bands because of the 3 plaquettes, and only one of them is flat. If we go to pi over 2, we lift this degeneracy, but still only one band is flat. But by going to pi, now all 3 bands are flat. And so we can operate this in a truly flat band system. So by stringing together these 2x2 plaquettes, we can emulate 3 unit cells of the rhombus lattice. And particularly at pi, it gets interesting. So what we have here is the same experiment now. We put an excitation on the left, and we look at what happens on these middle qubits from left to right. We vary the phase through all 3 loops between 0 and 2 pi. And of course, what's interesting is what happens at pi. And so what happens at phase pi is that, of course, this excitation returns to itself, but on the other qubits, very little of the excitation appears, right? And so this is essentially a result of this flat band system. One way we can think about it is in the context of conductivity, is that at pi, if we think of this excitation or the movement of the excitation as conductivity or an illustrative of conductivity, transport, it goes to 0 at this value of pi. Another way to look at it is localization, and the localization length gets very small near pi, meaning it's highly localized. And so we can start to do experiments like this where we look at the transport behavior in different systems. And here the intuition is that of course, in a flat band system, the velocity of the electron transport goes to 0. And so the electrons become highly localized and there's no conductivity. Okay, in the last few minutes, I'd like to talk about some high fidelity gates with fluxonium. Turn our attention a little bit here because it's important that we try to achieve as high an operational fidelity as possible, in part because that allows us to do more gates before we run out of time with our coherence, but also because high fidelity enables us to do better quantum error correction or sustained computation. So around 2023, we made this device. It's called fluxonium. I'll show a picture in a moment. It's one of the many types of superconducting qubits, and one on the left, one on the right, and it's coupled here by a tunable coupler. In this case, it is a transmon, but it's basically an on-off coupler. And we were able to get 2 qubit fidelities above 3 nines and single qubit fidelities above 4 nines. And the question we wanted to ask is, can we do better? And so here's what this fluxonium looks like. Fluxonium is a small Josephson junction in parallel with a large inductance. Now, this inductance is realized also by Josephson junctions in series, about 100 of them, but it's basically a linear inductance because those junctions are much larger. The nonlinear junction is this one right here. And we also put a shunt capacitance on it. And with this, we're able to get coherence times that exceed a millisecond, T1 times that exceed a millisecond. So there are 2 of those, and then there's a more conventional transmon here. This is what it looks like on a chip. You can see the 3 qubits here, 2 qubits and a coupler. The control lines are coming in, and these wiggly lines, those are the readout resonators, which we read out through this line here. Yeah. So for our single qubit fidelity, particularly for superconducting qubits, if we are coherence limited, there's really only a few ways we can improve fidelity. One is to increase the coherence times, of course, T1 and T5. And with fluxonium, those become fairly long. The second is to decrease the gate time. And so with long coherence times, you just make the gate faster and faster, and the fidelity should go up. It doesn't always do that. And the reason is that, particularly for qubits like fluxonium, which have relatively low frequencies, maybe 100 or 200 megahertz 0-1 transition, as we get our gate time down to 10 nanoseconds or even less, we start to break the rotating wave approximation because we're effectively driving very strongly in this limit. And we start to see coherent errors during the gate. And it matters for fluxonium because basically the fluxonium qubit frequency is 100 megahertz, and if our gate time is 10 nanoseconds, this is really what matters, is the product of these 2. And so what we did in this work is we had 2 complementary approaches to eliminating the counter-rotating errors that we see during Rabi-based driving or gates. And one is to co-rotate the drives, and 2 is commensurate pulsing. And in doing this, we were able to get almost to 5 nines fidelity, so almost another factor 10 in the error rate. Now, to do this, particularly the co-rotating drives, there's one other detail that I need to mention, which is that on this qubit, we can drive it in 2 ways. We can drive it capacitively, so we capacitively couple a drive line to the qubit. But we have a second drive line, and that drive line we can inductively couple to our qubit. Okay. And by doing this, we're able to drive both charge and flux simultaneously. And that's important because for us, we'll usually associate the inductive drive with a sigma X type driving along the X direction of the Bloch sphere. And capacitive coupling is 90 degrees out of phase. And so that couples to the Y axis, or sigma Y driving. So usually, when we drive qubits, we don't drive them both sigma X and sigma Y simultaneously. In almost all experiments that I'm aware of, including the ones that I just showed, we're driving along one axis. I drive it, say, capacitively. And we'll call that a linear drive because basically we're oscillating the field along this Y axis here. Of course, there's a qubit field, that's the qubit frequency. And the precession that happens is Larmor type precession around the qubit field. And then when we drive it, we get Rabi type precession around what we'll call the Rabi field, in this case along this Y axis. And what happens is that as our Rabi drive starts to get larger and larger compared to the qubit frequency, as we said before, that we're going to have variations that are due to breaking the rotating wave approximation. So the way that we were thinking about this is if you take a linear term, just a cosine, you can, of course, trivially break that up into these 2 components, one that is co-rotating with your qubit and one that is counter-rotating with respect to that. Okay. And this is, of course, what's really happening in our linear driving situation. So when we go to a rotating frame, we make one of these, we'll call it the co-rotating term, static, which means that the counter-rotating term is now rotating at twice omega, okay, twice the qubit frequency. And that's why we can get Rabi flopping around this static field. And because we're in the rotating frame, we've eliminated this qubit field. We're basically rotating at the qubit frequency, and that exactly eliminates that field. So the only precession we have is around this Rabi field. Okay, so the rotating wave approximation basically is just say, hey, let's ignore the counter-rotating term because it's going at such a high frequency that as we rotate around and do the Rabi flopping, it doesn't matter. But of course, as the Rabi flopping gets faster and faster, we can't ignore the counter-rotating field. So the question is, can we perform strong resonant driving without counter-rotating errors? And the answer is yes, because we can drive what we would call circularly polarized driving. And of course, with a free spin, like an electron or nuclear spin, this is something that we can do because X, Y, and Z in this case are the spatial dimensions X, Y, and Z. And we can drive with an electric field or in a magnetic field that is circularly polarized, meaning that the electromagnetic field will rotate around the direction of propagation. Okay, so that's something that's certainly possible with natural atoms. But in our case, because these couplings are not spatial dimensions, it's actually a capacitance and an inductance, we actually have to drive both simultaneously to achieve this. And so that's what we've done. We're driving both charge and phase simultaneously with the same strength, which of course we had to calibrate. So they have the same Rabi frequency, and we put a relative phase in here between them. Okay, and this is, as a function of that relative phase, or sorry, the vertical axis is the relative phase. Here is the duration of the pulse, and then we're plotting the population in one. And we can, of course, in this way, mimic linear driving if we choose the right phase, in this case, 180 degrees, then it's just linear driving again, and you can see the impact of the counter-rotating term. But importantly, we can choose a phase, in this case, 90 degrees, where we've basically eliminated the impact of the counter-rotating term. So we only see co-rotating dynamics, and so it looks much cleaner, as we would expect. Now, of course, we can go in the other direction, and as we approach 270 degrees, we're basically turning on more and more strongly the counter-rotating term and turning down the co-rotating term. So we have full control over this. But the one that we want to use for our experiment, of course, is the simple co-rotating case. So when we do that and we benchmark our coherence, or our fidelities, this line up here that's purple is the lowest measured coherence. The coherence times, it's a detail, but in these artificial atoms, they fluctuate because there are lots of environmental defects that fluctuate. And so what I'm plotting here is the lowest coherence times and the fidelity that we would expect from them. And what we see is we're still not quite limited by the coherence, which means we still have some control errors. Now, ideally, the circularly or co-rotating drive, the green, should be higher than the individual flux or charge drives that we show. So the orange and the blue are when we're driving only charge or only flux. But what we see is that for a reason we understand, the charge fidelity is a little bit lower than our flux. And that's because when we charge drive, we couple to higher excited states, even weakly at the 1 part in 10,000 level, but it impacts us here and reduces our fidelity, drives us out of the 0-1 manifold. And so this green circularly polarized fidelity is basically limited by the charge. And so it ends up being about the same as flux. Okay. So this outperforms charge. It does actually outperform flux if we get to even lower or faster pulses. But from a scalability standpoint, it's not great because it requires 2 coax lines. It's neat to be able to say that we can do circularly polarized driving, but not so practical. And so we wanted to ask, can we still go back to linear driving and do better? And the context here, I'll pick it up a little bit because I know I'm coming to the end of the hour, is something called commensurate driving, which reminds me, I mentioned earlier, the Landau-Zener type dynamics, is we're starting to get into that limit where it's really Landau-Zener-like in a sense, very fast dynamics. And in fact, the Nobel Prize was awarded a couple years ago precisely for this situation where there's, driving at, very, very fast optical pulses, much faster than the period. And what we see then is something called carrier envelope phase, where the, sorry, somebody's ringing my doorbell here. They'll come in a moment and I'll tell them to leave. So the carrier then, the period of your carrier is on the order of, say, the Larmor precession. And what happens then is that when you time the carrier with respect to the envelope becomes very important. And it becomes important because we know Rabi driving, the degree or the amount of rotation we get is related to the area under the pulse, or the energy that we have there. And if we look at Rabi rotation angle as a function of where this pulse starts relative to the carrier, then what we see is that there's actually quite a difference in terms of what rotation we actually get. Now, typically, with, say, a qubit like a transmon, where it's at 5 gigahertz and it's a 10 nanosecond pulse, we're down in this regime where it just doesn't matter. There's so many oscillations within a single envelope that changing the carrier envelope phase has very, very little, meaning 1 part in, say, 10 to the 3 or 10 to the 4 impact on the rotation angle. But for qubits like fluxonium, or when we drive very quickly with respect to the Larmor period, this becomes a substantial error. And so the answer is just to make the pulses commensurate, meaning that the pulses always line up on the half period of the Larmor period, or that, the half a Larmor period. So what's shown here are commensurate pulses. They look symmetric to one another, both X and Y pulses. This is incommensurate. This is when we don't do that, right? And you can see that the area just visually looks quite different. So when we use a commensurate pulsing, now things become much, much better. And in fact, we're able to approach these fidelities of 99.998%, 7 to 8%, and appreciate that we're very honest and our students are very honest. And we didn't quite reach 5 nines, and we're working to do that. And of course, it's much better than the incommensurate pulsing that we see here. So with that, the net results are shown here. The highest and lowest measured coherence, and down to around 10 nanosecond pulses, we are able to, with our flux driving, maybe even a little bit less, with commensurate driving, we're able to get basically coherence limited performance, which is what we wanted to achieve. We still have some improvements. If we go to even faster pulses, we now have some coherent errors kicking in that we need to fix. But this is indicative of being able to achieve coherence limited driving. Okay. So Sergey, I'm at 10 o'clock. Should I stop? I have 3 more slides.
Very nice. Please go ahead.
Okay, I just want to finish up because it is the International Year of Quantum, and I wanted to mention that, a fantastic experiment that happened last fall from Google Quantum AI related to error correction. The qubits that I just talked about are physical qubits, and they have error rates of 1 in 100 to 1 in 10,000. I just mentioned how we got close to 1 in 100,000. Heroic, right? We're all trying really hard to improve this. But for practical applications, we'll need 1 billion or even 1 trillion operations. And so we need much, much lower gate errors. We need to be in this blue range. And this chasm is quite large. By the way, a CMOS transistor has an error rate of 1 part in 10 to the 20, right? That's why these computers are so good today, classical computers. And fortunately, we don't need to be that good, but we do need to be much better than where we are today. And of course, the answer to doing this is to create logical qubits or teams of qubits that perform according to some algorithm better than their physical constituents. And so this is a physical qubit, a transmon. This is a logical qubit called SURF17. There are 17 total qubits. 9 of them store the quantum information, And then the other 8 in blue are basically referees that check where an error may have occurred. And of course, if you ask, what is the error per cycle on this logical qubit rather than a single physical qubit, you would expect that it should get worse. And it does. There is a cost, C, to doing it because there are more qubits, right? And we have to perform more gates, right? But in performing the algorithm, there's also a benefit. The error correcting code improves our overall error rate. And it improves it exponentially. And that is both the goal and the promise of quantum error correction, is that even though you pay a penalty to go to more qubits, the win is exponentially large. And so that means that going from distance 3 code to, say, a distance 5, distance just counts the number on the edge that are data qubits. You go to more qubits, but this error rate should go down if you're beyond threshold. So what threshold means is basically this crossing point here where my individual qubits are good enough that going to more qubits actually makes the situation better. And you know, I use the analogy of my son when he was in kindergarten. You know, he wasn't very performant. You go to the playground, they have a lot of fun, but adding more kids to the playground is just more chaos. But at some point, he grew up, and as he gets older and older and more mature, now he can form teams, math team, science team, and together as a team, they outperform any individual. And that's basically what happens when you cross threshold with qubits, is that adding more qubits, things get better. And it gets exponentially better. So the cost is over here, but once you get better than that cost, you get this exponential scaling. And in going from a distance 3 to distance 5, you get this improvement lambda. Going to 7, you get the same improvement. And of course, this continues on and on and on. And if you need to get down to, say, 1 part in a billion or so error rates, then you can do that. Distance 17 or distance 19 error correcting codes. Right. Distance 17 has 577 total qubits. Distance 25 would be well below this level, has around 1,000 or 1,200. So with just going up by a factor, you know, just over 20 or 30 here in qubits, you reduce the error by a factor 500,000. That's the promise, right? And at the distance 17, you get an error rate of 4 times 10 to the minus 9. Okay. Now, the physical error rate of those qubits is 2 qubit gates, still around the 0.1% level. And there's still a huge win for us to improve the physical qubits. So just a factor 2 improvement here translates to better than a factor 10 improvement in the logical error rate at the same size. So we still want to improve our physical qubits, and doing so gives us even more of a win overall. So that leads us to the Google experiment from last fall on the Willow chip. This chart is a little complicated, but what's plotted here is the logical error probability as a function of the number of error correcting cycles. They basically set up a memory, and they just kept interrogating it, checking for errors, and coming back. And they did this a total of 250 times. They ran the error correction cycle 250 times, and they asked, what's the error? And for a distance 3 code in red, this was the error rate shown here. And when they went to distance 5, it got more than 2 times better. And when they went to distance 7, it again got another 2 times better, actually 2.2. And what's very interesting is that if you look at the best physical qubit, that's plotted here in green. So by going to distance 5 or to distance 7, the logical qubit is now performing all of the qubits that make up the logical qubit, even the best one, right? So what Google did is showed for the first time on any hardware platform that increasing the number of qubits shows this improvement that we expect, going from 3 to 5 to 7. I also want to highlight that many other error detection schemes have been done encoding logical qubits in neutral atoms and other superconducting and trapped ion systems as well. But this was the first time that this scaling was shown. And this is what we have to do because we need a lot more qubits if we're going to realize the promise of quantum computing. So with that, let me end and acknowledge my teams. First off, at the MIT campus, the Engineering Quantum Systems group, and also our sister group out at MIT's Lincoln Laboratory, and also the many sponsors who made the work possible. And thank you for your attention.
William, many thanks for your impressive talk about your nice work. And me in particular, I appreciated the modeling and simulations which describe such complicated experiments. But I understand that the experimental work is tremendous you did. I would like to ask the audience about questions and comments. Andrei Sotnikov, please.
Thank you very much for a wonderful talk. I have a question to clarify correspondence to the Bose-Hubbard model that was eliminated. Is it correct that this is always half-field model for your case? So you have one boson per site, or
Yes.
And with this excitation, you kind of mark the boson in this chain, or not? How I can
you said sorry, the last thing I didn't quite catch. You said, can I mark it? Did you say, or?
Yeah, this excitation. So you track how excitation then travels on the chain or across the lattice, right? So is it the same boson, or it's kind of distinguishable boson then, if you excite a particular?
Oh, I think in this case, so in the single case, it's of course distinguishable because there's only one, and we can follow it around. But and I didn't talk about it today, but we've done experiments where we make multiple excitations. On a 16-qubit lattice, we can do, of course, up to 16 excitations. But then, because of the hardcore limit, we never, in this case, will get two excitations on the same site. So everything basically is frozen at that point. But if we increase the exchange energy, we can, of course, get two excitations on a site. And I have a student who's working on this now to actually realize, say, a doublon or a two excitation site. And then we could have up to 16 of those double excitations. And I think things get quite interesting here. But on a single site, if I have two excitations, then I don't know that I can distinguish them, right? Because they're on the same site. Yeah, and it looks like two bosons in this sense. Yeah.
Is it then that you can study some kind of BC crossover regimes with your system as well?
That is certainly what we're hoping to do eventually. Yeah, and the first experiment that Sarah is working on is to do a mod insulator superfluid type transition. And I think from there, we'll see how far we can take this. Now, one limitation, and it's a serious limitation, is that 16 is certainly not a many-body system, right? So when we say that we want to do mod insulator superfluid transition, basically we're numerically simulating what that would give with a very limited number of sites, meaning only 16. And you can see some trends that look like that eventually for a large number or an infinite number of particles would become a phase transition, but at only 16, primarily due to edge effects, right? It's not so sharp. But we can see the trends, and we can say that, okay, this is what you would expect to see if you did it in a system with only 16 sites, or maybe only 25 sites as we increase the size. But we're definitely, I would love to do it with more and more sites. But it turns out, the electronics becomes very expensive. And of course, we have to develop the calibration techniques. And even the companies like Google, they're working with 100 or 200 qubits. And of course, they have very large teams there and at IBM. So maybe one day we could try it on their systems. In the meantime, we can show consistency between numerical simulation and what we measure.
If I may, I have a couple of short questions in addition to this. So is it possible then to go to realize somehow a whole doping in the model, or this is not the case?
We'd have to think about that. I don't know exactly off the top of my head. There may be a way to do it if you somehow offset particle number so that, removing one looks like a hole and adding one looks like an electron, and then, but I'm sure it would involve playing some kind of trick like that, where you start maybe at half filling and then subtract or add to it.
And the last question on the sign of interaction, is it possible to go to repulsive side? Did you think about the repulsive interaction?
Absolutely, yeah. That one is actually a little bit easier for us because different types of qubits would have different types of anharmonicity. And one of them, say like a flux qubit or fluxonium, you can actually tune the sign of the interaction. You can design a qubit where at one flux bias it's positive and at another flux bias it's a negative interaction. So we can even tune it in situ. It doesn't even have to be static. So that's one of the earlier things we would like to demonstrate.
Thank you. Thank you.
Yeah, thank you for the question.
Professor Andrei Zvagin, please.
Thank you very much. Thank you very much for your interesting talk. And I have a very special kind of question. You said about that you study the system of bosons with harmonicities, and whether it is possible to observe some parametric instability in your system.
And what kind of parametric instability are you thinking of, for example?
I mean that if you have anharmonicities of any kind of anharmonicities, then for the standard system of bosons, you would observe the situation in which if your magnitude of your applied pumping, let's say, is larger than the relaxation rate in your system, and it is, as I understand, it is the case in your situation. You should observe some parametric instability. The number of bosons will grow exponentially. Have you ever observed this kind of
I don't believe we've observed it. And in this case, the pumping is a direct pumping of excitations into the lattice as a whole, or is it on a single site that you would expect this increase to occur?
Okay, thank you.
Okay, yeah, I think I would need to look into it a little bit more to understand the parameters. I'm wondering if it's on a single site or whether it's across the entire lattice. Because we're in the hardcore limit, we have excited up to 16 excitations across the whole lattice, but I don't think we've seen the type of, I don't know, I need to understand more what this parametric effect that you're describing is, yeah.
And the next question from Andrei.
Thank you very much.
Okay, first of all, thank you so much for very interesting talk. And I have a question not connect with your talk. And this question is about Microsoft processor. What do you think about a new Microsoft processor based on Majorana quasi-particles? What is your opinion? Thank you so much.
Will you mention?
Yeah. So I think that this is very interesting scientific research for sure, that trying to get Majorana excitation at the two ends of the wire is quite interesting. And, Microsoft has spent a tremendous amount of effort trying to achieve this. And their recent paper that they published, I think, shows some evidence of it again. And what they didn't publish yet, but they showed it at the APS March meeting, and also they've shown it to some other people, seems to indicate signatures of basically signatures of measurements that look like an X gate and look like a Z gate, with fidelities that aren't very high, but for the first time, okay, at least those can be identified, maybe 50%, 80% type fidelity. So I think they are making progress. Of course, then the publicity side, where they, release the Majorana 1 chip and talk about how it can support up to 1 million Majorana qubits, I think that is what it is. It's aspirational, that they look to this to be a pathway going forward. But today I think they're still focusing on demonstrating a single qubit, and I hope that they can do it, because I think it's really interesting physics, and I'm glad somebody's looking at it.
Okay, thank you so much.
Thank you.
I would like to ask you two questions about the arrays of transmons, which were in this first half of your presentation. You have pretty weak couplings, only 6 megahertz. I guess it's enough to win relaxation and decoherence. Still, it might be an order of 2 higher, right?
Yeah, so it's sufficient, but it was smaller than we desired, and so the follow-on chips. What I was showing here, basically stuff that we've published over the last couple of years, but our more recent chips, we've increased that coupling strength by about a factor 5 or so.
And what if the coupling is not weak but rather strong? What?
Well, if we can make it strong, then of course we could get out of this this single excitation limit, and get out of the hardcore limit, so that we can now have multiple excitations, especially if J can be larger than the on-site interaction U.
Will you not be able to study new solid-state phenomena if you have strong or ultra-strong coupling?
Oh, if we go to ultra-strong level, then yeah, that could be quite interesting, because of course, I think as you're suggesting, that if it gets even at the size of the on-site energy of the qubit, then this model of having 16 different qubits or 25 different qubits, it's no longer perturbative correction to those qubits, but it becomes basically one system. I think maybe that's what you're suggesting, and I do think that's quite interesting, yeah.
And my second out of 2 questions is about what you measure. When you show that n is in the range between 0 and 1, does it mean that all the qubits have excitations in this range? I mean, don't you have leakage to higher levels in transmons? Don't you have increases of these populations when you have interference, constructive interference in Aronoff ball and other situations?
Yeah, so in this case, in those experiments, there's just one excitation, and we create that excitation using a conventional gate, say pi pulse. And we tune the pi pulse so that we implement it in a way that there's essentially no leakage to the higher states. So once we have that excitation, everything else is just dynamics of the system. It's basically following its Hamiltonian dynamics at that point going forward. And because the J is so much smaller than the U, there's no escaping into to a higher level, to a very, very good approximation. So that's number one. So there's no leakage in practice. Then the second thing is that when we run these experiments, of course, and we make a measurement, it's a projective measurement of 0 or 1. And so we have to run the experiments many, many times and take an ensemble average. And that's how we get numbers between 0 and 1 for each site. But to be clear, we're measuring each site every cycle every experiment, and recording the zeros or the ones, and then we average all of those together site by site, so that we can say on site 1, on average, there was half a excitation. On site 2, it was 0. On site 3, it was 1. On site 4, it was whatever. And that's how we come up with these numbers. Yeah. But it's always a measurement of every qubit individually and recording the zeros and the ones that we see.
Thank you. Oleg Turtanov, please. Next question.
Thank you very much for your report. Such a question. Is there any tendency in development of new qubits with unharmonicity? Is there a tendency of making it higher or lower?
Yes, indeed. And I didn't mention it, I think, but the fluxonium qubit that I showed at the end has a very large anharmonicity, actually. So the 0-1 transition frequency, say, is 100 megahertz or 200 megahertz. But the 1 to 2 transition may be 4 or even 5 gigahertz, so much larger. And if you go back to the first qubits made in the early 2000s, the flux qubit or the charge qubit, these also had very high anharmonicities, similar sizes. And it's just that when we moved to the transmon as a community, that move was made to solve some other problems, charge noise, for example. So the transmon is a capacitively shunted charge qubit. So basically took away the charge sensitivity. But in doing that, the qubit became much less like a double well potential and much more like a harmonic oscillator, right? And so then this is when we went into the regime of very, very low anharmonicities. But because of the noise improvements, the qubits actually worked a lot better. And so for a long time, people have just used this low anharmonicity transmon type qubit. But recently, with fluxonium in particular, we're now back to a very clear double well potential with very large anharmonicity, but the coherence times can be quite long as well. And so in my group, for example, we're doing both transmons and fluxonium. And we like the fluxonium because it has this large anharmonicity. And in fact, it's a tunable anharmonicity to get both signs of the on-site interaction, plus and minus, attractive and repulsive.
Thank you very much.
Thank you.
Last call. More questions or comments? Yes, Oleg Ivakhnenko from Japan. He doesn't sleep.
I have one question about Landau-Zinner type gates for quantum computing. What do you think about perspective of these gates? Recently, I also wrote a fully theoretical article on this subject. It seems quite interesting.
Yeah, I'm quite excited about it. I would say I think it's we want to operate as quickly as possible, and so we're moving into this limit, right, of true Hamiltonian dynamics and wave function dynamics in driving qubits. So I think it's a very interesting direction to go. And the faster we get, the closer we get to that limit. And so from my perspective, it's quite useful to think of it in those terms first, and then relax the assumptions of, say, the pure Landau-Zinner type quantum interference at avoided crossings, and use this to implement fast, non-adiabatic or partially non-adiabatic control.
Thank you.
Thank you. Oleg is thinking about his future projects, and one of the possibilities would be to continue this work on optimization LZSM like non-commensurate, as you say, gates.
I think it's great. Ola, if you would like to reach out, and maybe we can do some experiments related to the theory that you develop.
Yeah, it would be very nice.
That's what we are
Good.
dreaming.
Okay, well, let's be in touch then for sure.
Thank you, Will, so much for the nice presentation of your impressive and advanced works. Have a nice day.
Well, thank you, Sergey, and all. It was my pleasure to speak to you, and thank you for the invitation. And I also wish you a good day.
Thank you.
Thank you. Cheers.
Thanks all the participants. Bye-bye. See you in 2 weeks, in some 2 weeks on the next seminar.
Goodbye.